All right, it wasn't my intention to use two different GABA drugs in the same exam, but it just turned out that way. And it turned out that way because I actually had this particular molecule prescribed for one of my animals recently. And so I looked it up, and here we are. So, this one's made a little differently because it's not structurally as similar as pregabalin was. This one actually has a ring as part of it, and that ring is generally there as part of the precursor. Because why would you want to make a ring like that if you didn't have to? And in fact, this is actually a relatively simple and straightforward conversion of an anhydride to an amide. That only one of the two carbonyl groups of an anhydride ends up as the amide, the other is the carboxylic acid. You know this already. I should have used this on the last exam, but I didn't. Okay, because I didn't look it up until now. So, the next part is a little different, and that is the chain is cut down. This isn't just reduction of an amide, it's actually one carbon shorter. And with bromine and sodium hydroxide, that's a Hoffman rearrangement to make an amine that is one carbon shorter. It's a primary amine always, it has to be because of the mechanism. But the point is, these conditions with an amide are Hoffman rearrangement conditions, and that is we lose carbon dioxide as part of it. From the first look at it, that's not entirely clear. What I had said here below that was you can basically abbreviate all this stuff if you need to, just to make it a little easier to see, because otherwise it gets a little visually ugly. So let's do that. So I'm going to basically just abbreviate a lot of stuff here to make my life easy. So I had this, and I had this. So we're just going to abbreviate that as this. Since that's the only part of the molecule doing anything. Okay, well, actually we're going to abbreviate it like this, since that's the only part of the molecule doing anything. Now, this reaction starts with sodium hydroxide deprotonating the amide. These are fairly acidic hydrogens, so this is not unreasonable. We get an anion, and then that attacks bromine, very much like an alkene did in the past. So we end up with bromination of the nitrogen. Like so. Now, we then have a second deprotonation. Which gets me here. The lone pair on the nitrogen was still there from here. I just didn't draw it because it was getting in the way. So at the point where we have an anion here, there are two lone pairs on the nitrogen. There's still a lone pair here. There's another lone pair there. So this is the problem, that this is an anionic nitrogen. So the Hoffman rearrangement begins from that, the rearrangement part anyway. And that is, we're here, we have our nitrogen with a negative charge on it, or two lone pairs. So what we're going to do is one of those is going to come inward towards the carbonyl. The R group is going to shift to the nitrogen and take its electrons with it. And the bromine is going to leave. Now, that is an ugly 1, 2, 3. So, but that is what happens. And if we draw that, we end up here. We end up with the carbonyl group unchanged, only it has nothing on its left anymore. We were forming a second bond between the nitrogen and the carbonyl. So we have that. And then the R group moved down to here, to the nitrogen. And the nitrogen still has one lone pair. So this functional group is called an isocyanate. And in the presence of hydroxide, that carbonyl is pretty reactive. So we're going to attack it nucleophilically, like so. And that's going to break the bond to the nitrogen. So we're going to get this. Where now I'm going to have that oddity of yet another double lone pair nitrogen. I now have the central carbon still with a pi bond to the oxygen. And now I have an OH group here. Now it's a question of what happens first. Probably this is going to go first, that we're going to protonate the nitrogen. So where there's hydroxide, there's water, and water would have been formed when it deprotonated anything. So that's going to neutralize the nitrogen, give me a normal amide on one side, and a carboxylic acid on the other. So we still have a base, though, and that's a very acidic hydrogen. So this is going to get ripped off. Now, some books will draw this all in one step. I'm not going to do that, just so you can see what's happening here. So I'm going to make this a little bit more symmetrical looking for the moment. So if I just looked at it as deprotonation happening by itself, rather than setting off the cascade, this is kind of like the malonic ester in that we deprotonate to this carboxylate, which then spontaneously will lose carbon dioxide. So this is what happens. So we form carbon dioxide. We then end up giving those electrons to the nitrogen. So that puts me over here. I now have this. And I have the nitrogen again with two lone pairs as an anion again. And carbon dioxide, which has left the reaction. We still have water here, so the nitrogen can be protonated very easily. So here we are. This is my amine. Now if I go back and put everything back that I used to abbreviate for R, I've got that cyclohexane, I've got the other carboxylic acid over here, and I now have, instead of two carbons, I only have the one and the amine. One carbon shorter chain from the original amide. That's the point of the Hoffman rearrangement, that we shorten the chain to lose carbon dioxide.